Hey guys, Rudi here with another CSSE1001 and 7030 tutorial solution video. So this week we're going to be looking at the week 12 tutorial, which was on complexity. Okay, it's quite a short tutorial, but it's got some important concepts that'll hold more so into the future years of your computer science studies. So complexity is sort of about basically up until this point, right? We've written solutions to problems, and we've basically just tried to get to a point where we have a working solution, right? We had a problem and we write some code and the code solves the problem and we're happy with that. Okay? But obviously some solutions are going to be a lot faster than others. Okay? And that's sort of where this idea of complexity comes into. Complexity is basically about us determining how well our algorithm will scale with the size of the problem. Okay? So when I talk about the size of the problem, say we're writing something that sorts a list of numbers, say, okay? There's lots and lots of different ways to sort a list of numbers, okay? But as the list gets really, really, really big, right? So say we've got like a list that now has 10,000 numbers in it, right? Some algorithms are going to sort that list faster than others. And so now we're going to try and start to think a little bit more cleverly about the design we can use when we try and solve a problem, right? And so that's all what complexity is about. Complexity is basically looking at an algorithm and going, how well will this algorithm scale with the size of the problem? So you can check out the course notes here for complexity and computability. You can just head to the website and check those out. But I'm not going to go into sort of as much detail as these things are talking about, but we're just going to work through the tutorial and sort of analyze the problems as we go. The gist of these problems, though, is generally the sort of algorithms we'll be looking at will fall into one of these kind of categories, right? We've got constant time for our complexity, and what that constant time basically means is regardless of how big our problem gets, the algorithm takes a constant amount of time, right? So let's say our algorithm takes 10 seconds or something, and then regardless of how big our list gets, we're saying no, we don't care how big the list is, it's always going to take 10 seconds. It's constant time, it's irrelevant. Constant is generally the best, but it's almost always impossible to get constant time for some things, right? There's no way that we can go like, oh yeah, let's just sort a list of numbers in constant time regardless of how big the list of numbers is, right? If the list of numbers gets really big, you're obviously going to have to spend more time. Okay, we've also got some other ones here, logarithmic, linear. Linear is one of the most common ones. Think about something like finding the biggest number in a list, right? The easiest way to go through it is to go through every single element in the list and be like, is this the biggest one? Is this the biggest one? Is this the biggest one, right? So since we're going through every single element in the list, right, we can see that as our list gets bigger, the time our algorithm takes is going to scale linearly with how big that list is, right? So in other words, say we had some list here and we're trying to find the biggest number, whatever, okay? If we say that this list is n long, right? Say it's got n elements in it. Okay. We can say that the time that algorithm is going to take is going to scale linearly with n, right? Because n is how big our list is, right? And so the bigger our list gets, the more likely, the longer our algorithm is going to take, right? We'll look at some of these other things like quadratic and logarithmic as we go. But I think it's going to be easier if we just get into the tute solutions before trying to explain too much about this. Okay, so uniquify. For this task, we want to write a function which removes duplicates from a list. And we're going to use this to analyze some stuff about complexity. So we're going to write a function, uniquify. Okay, which takes a list and returns a list containing each element of items without any duplicates of the items. So we got an example here, and we can see that it's stripped out the duplicate 8, the duplicate 5s, right? It's just stripped them out. Okay. So, well, let's think about the sort of easiest way we want to do this is we're probably going to have some sort of results list, right? That we're gonna build up with only unique items as we go. So, okay, basically let's have a think about this. What we're gonna do, we're gonna loop over our items, in items. Okay. And then I suppose what we'd basically want to do is we would just want to add our items into append, right? But we don't want to append every single item, right? We only want to append an item if it's unique. So we need to have some sort of check here, which is basically if item is unique, then we want to add it into our results list, right? Now, in terms of determining uniqueness, this one's not too complicated, right? Because we know that results contains all the items that we've already added, right? Because we're just going to go, okay, cool. If it's unique, add it in. And the easiest way to see if an item's unique, right, is just to go, well, have we added it before, right? Because if we hit a number in this list, say we hit this 8, and we know we haven't already added an 8 into our result, then we can assume for the moment that that 8 is unique, right? Because later down the track, if we find a second 8, we can just not add that one because that's the one that's making it not unique. So all we can really need to think about here is if that item is in result. And by in result, I of course mean not in result. Yeah, there we go. Okay, because we basically got here, if the item's not already in result, we add it into result. And if it is in result, then we don't want to add it, right? So say here we have this 8. We find this 8. We go, have we already added an 8 before? No. Add it in. Have we found a 3 before? No. Add it in. Have we found a 5 before? No. Add it in. And then we hit this 8 here and we go, have we found it before? And we go, yes, it's already in result. So we don't bother to add it, right? And so this is one of the easiest ways to check as we go. Okay, so if item is unique, in other words, if it's not there, then we're just going to append that. And then once we're done looking through every single item, we can just return our result guy. Okay, so let's quickly give this a run. And what was that example we had there? Uniquify this stuff. Cool, and we can see that it has indeed stripped out some of those duplicates for us. Cool, so that's working. But now, right, we're not just going to go, cool, that's working, we're done. We're going to look at the complexity of this algorithm and see if we can try and do better. We'll see what's happening here. So in terms of complexity, right, items is the thing that is scaling, or items is our list, right? So the bigger our list gets, we want to know what happens with our algorithm. So let's see here. Items, the way we generally try and approach these sort of problems is we consider items to be something that is n items long, okay? That way we can sort of work with n and try and do some maths there. So for item in items, right? Well, we know that there's n things in items, right? So this line here is going to happen n times, right? Because for every single item, we look at it and we do some stuff. And for there we go, okay, cool. Well, every time we look at one of these, we got n of them. So we look at stuff n times. Now let's look a bit deeper here. If item not in result. Now, initially, this can be a bit confusing, but let's think about how this in part works. In order to determine if an item is in a list, what we actually do is Python actually under the hood checks this item against every single thing inside result, right? It basically lines up the result list and it goes, well, is item the first guy? Is item the second guy? Is item the third guy? And if it determines that item is none of those guys, then it tells you, cool, it's not in it, we're good. So we got to always think about, when we're doing our complexity, we're always trying to think about the worst possible case for our algorithm, right? The slowest it could get. Because it's all well and, it's all fun and games to be like, oh, cool, my algorithm could theoretically do this in like one step and, it'd be awesome if the list looks exactly like this. But that doesn't really help us because we don't know what the list looks like, right? So we always want to assume the absolute worst. In this case, if we have an entirely unique list that we pass into Uniquify, right, then we're doing a whole bunch of work and we're never, ever gonna break out of this, right? We're always gonna be doing all the work and then getting to the end and being like, cool, we'll check the next one. Is it unique? Check all of them, right? And it's never gonna find something that's not unique. So we're never actually gonna sort of skip out, right? In this sense, we need to think about, well, what's the worst sort of time that this could take? And since we know that item is being compared to every single thing inside result, the question here basically becomes, well, how big can result be? Okay? Now, in the event that items is an entirely unique list, right? When we get through the end, right, and we're going through the last time, this result list is going to contain almost every single element inside items, right? It's just going to be missing maybe the absolute last one. So result can actually get up to size n. Okay? So in order to compare item with everything in result, this thing is actually going to also take n times. So if you want to think about it, it's going to be proportional to how long n is. Okay? Now, since we've got these loops nested, we know that this loop happens n times. And within this loop, this statement here also happens in n time, or in other words, linear time, right? Linear with n. So the sort of time complexity of this guy overall turns into an n times n, right? Because for every n times, we have to do something that takes n time, okay? So we get something that's sort of proportional to n squared. In other words, this algorithm at the moment is on what we call quadratic time, because it's n times n, so it's n squared. In other words, what you can think of is if we were to double the length of our list, the time is going to take, well, we doubled it, so we times it by 2. And since this is a quadratic time, it's actually going to increase by 2 squared, or 4 times in time. Okay, so in other words, if we try this with a list that's 10,000 long, and then we tried it with a list that was 20,000 long, we can expect it to take roughly 4 times as long, right? And so we can see that this algorithm doesn't scale very well, right? Because as n gets really big, we're constantly sort of squaring the amount of time it takes, and it's just going to get bigger and bigger and bigger and out of hand really quickly. So if we can, we really want to try and think of a sort of better way of looking at this. Or at least to try and get it smaller than quadratic time, right? Something a bit more efficient. So we're going to look at this next part. Discuss how the complexity could be improved if the items list was sorted to begin with. Okay? Write a function uniqueify to which, where'd I go? Which removes duplicates by first sorting the list. Okay? Hint, sorted items will give a copy of items in sorted order. So we're going to want to be using this for our items, because we're going to try and sort it first, but then we're going to try and write a slightly better algorithm. So we're going to want to set up our result guy again. And this time, instead of using items, we're going to use, I don't know, sorted items. Ah, that's such a bad name, whatever. Sorted items, right? This is the guy we're going to be looping over. Because now we're going to step through every item in our sorted items, and now we're going to try and do some stuff. So let's think about this. We're trying to write a more efficient algorithm, right? Based on this sorting algorithm that we've got here. So based on this sorted algorithm we've got here, we need to think, well, if the items are all in order, is there a way that we can be more efficient than how we were in our last algorithm here, right? So let's just start off with this. And let's just see if we can try and improve on this based on the fact that our list is now sorted, right? So let's see. What we were doing before is we were going, cool, for every item in our items, we were going, is it in the results? In other words, we compared it to every other element that we'd already checked and was in results. Now, since our list of items is sorted, right, that means we now have something that looks a bit like, 9, 10, 20, whatever, right? We've got something that's sorted like this. So let's say we're going along and we hit this 9, right? And we want to know if this 9 is unique. Is it really necessary anymore to check every single element up until that 9 to know if that 9 is unique? Or this 7, for instance. And the answer is no now, right? Because we know that our list is sorted. So for instance, let's say I'm going along and I'm checking the elements beforehand. Let's say I check this 5, right? Because I'm checking the 7, right? But let's say I get to the point where I'm going, cool, is the 7 in the list? Check this number here. And I go, well, this number's a 5. So what at this point here, what do I know about every single element before the 5? Well, we know it's either 5 itself, right? Like there could be multiple 5s in a row, or we know that it's less than 5. So in other words, if we wanted to find a number that was bigger than 5, we have no reason to check any element prior to that 5. Okay. Similarly, if we're trying to check if this 7 here is unique, right? The only number we actually have to check is the number directly before the 7. Because let's think about this. Let's look at this 5. If we know that the number directly before it was a 5, what do we know about every single number before the 5? Well, we know it must be less than or equal to 5, right? And if it's less than or equal to 5, it wasn't another 7. So if we check the 7 and we go, oh, cool, there was a 5 before us, then all we need to know is, okay, well, this number's less than 7, so all of these must be less than 7, so this 7 must be the first time we found a 7, and therefore it's unique at the moment, right? But for instance, if we hit the second 7 and we check the number before it and we go, is it the same number? And we go, yep. Well, we go, well, cool, we've already found a 7, right? And in this way, we're sort of enabling us to forget all the checks that we were doing on every single number before this, and we've completely replaced it with only a single check. All we need to do is check the number directly before it, right? So let's think about how we would sort of set this up in the code. We're going for item in our sorted items. Now, all we need to do here is we don't need to check the entirety of result anymore. All we need to check at the moment is that item is not equal to the one before it. Okay. Now let's think about what the one before it means in this context. If the one before it, right, was unique, or the last thing that we checked before it was unique, it's just going to be whatever's at the end of results, right? Because, well, if it was unique, we chucked it into results. And if it wasn't unique, right, then we already had something in there that's the same. So all we need to check is if result is not equal, if the item is not equal to the last thing in results. Okay, so let's say we're stepping along, we hit this 7. Well, what's the last thing in our result going to be? It would be this 5, right? Because we would have added the 5. But let's say we check this 9, right? The last thing we would have added to result would have been, well, it would have been one of these 7s, right? Because the first 7 was unique, right? So we would have added the 7 in. And in this case, we don't really care which 7 it was, right? It's still a 7, and we know, well, 7's less than 9, so 9 must be new. Okay, so this is the only thing we actually have to check here. Okay, so let's just try running this and seeing what happens with our sorted items now. Okay, so what did we run last time? We ran uniqueify. So let's try running uniqueify 2 and see what happens. Oh, we got some red here. If item not equal to result -1, list index out of range. Okay, so Python's telling me that this result -1 was an index out of range. Okay, now since -1, if you remember your string indexing, or your list indexing in this case, -1 gives us the last element in the list. So the only way that the last element in the list could be out of range is if our list is empty, right? And if we actually sort of think about the very first time we step through this algorithm, our results list guy is going to be empty. Okay, so we need to have two sort of checks here. We need to check either that this is the case, or if our result is empty, right? What do we want to do? If we have nothing in our results, we'd always just want to add the first thing, right? Because we know it's guaranteed to be unique so far, because we don't have anything. Okay, so we need to add some sort of check here, which basically goes, well, if len of result equals 0, or, wait, no, not or, and this is the case, right? Then we're fine. Wait, do I want that to be an and? Maybe I do want that to be an or. If the result is equal to 0, yep, or item not equal to results, then we're fine, right? Because we basically go, cool, is our result list empty? Cool, add something. Otherwise, we go, well, is this the case? Yep, then add something. So let's save this and let's try running this one now. And yep, we can see that we've got only unique numbers. And you also notice that it's sorted now, right? Because our sorted items was doing some sorting for us. Okay, now let's look at the time complexity for this guy. We know from last time that this step here takes n counts, right? Because we're looking at every single item in items. And if we go back to the chute, which one's the chute? Is it this one? Yep. If we go back to the chute, it tells us without modifying the little list, sorted runs in n log n time. Okay, so we know that this step here takes n log n time, right? So n times log n. Okay, which is obviously slightly longer than just normal n time. But let's look at what happened last time, right? This thing here was the thing that gave us problems. So last time we were checking every item in result, and that was going to be linear time. But let's see what we're doing here. We're checking if the length of something is 0. Well, we know what the length of a list is just by typing len, right? That's an instant operation. That's constant time. So this guy is a constant time, right? Or a 1 count, if you want to think about it that way. And this guy here, we're only checking one element in the list. So that's also a 1 count. So this whole thing here is a constant, right? It's only going to take 1 or 2 counts. And we don't care about whether it's 1 or 2 or 7 or 9, right? Because all we need to know is that it doesn't matter how big our list gets. This is still always going to take a constant number of counts. So this thing here is constant time. Okay, so if we were to sort of try and count up again the complexity here, we could go, cool, well, this first thing is n log n. And then this second section here is we're doing this loop n times. And every time through the loop, we're doing something a constant number of times. So in other words, this is n times 1, if you want to think about it that way. Or just n, really, because this whole loop is just linear, right? It's basically going to be with, this is the thing that determines how big it is. Now, if we look at these guys here, the only thing we're really interested in is the worst of these, right? We're not going to say that this is n log n plus n time. We don't really care about that. We care about the worst one, right? And obviously here, n log n is slightly bigger than n, right? As n gets really big, this is going to be the term, this is going to be the term that sort of dominates it, okay? So in other words, this thing is n log n time. Typing n log n time complexity. Okay, and we can see that n log n is going to be faster than n squared quadratic time, right? Because this guy is n times n, whereas this guy is n times log n, and log n is much faster than n, right? Log is normally something we want to aim for. So that's good so far, right? So let's look at the last one. In this course, we have already encountered a data type which contains a notion of uniqueness. Discuss how to use this to write a function uniqueify3, which does the same task but even better time complexity. Okay. Can never type that. Uniqueify 3 items. Okay. Now this thing it's talking about here, a data type which contains a notion of uniqueness. Now that would be your dictionary, right? Because we've used dictionaries before, and we know that if we ever try and override the keys in a dictionary, it doesn't keep adding extra keys to the dictionary, right? It sort of just overwrites them. So I'm just going to put a pass here for now. If I have a dictionary over here, and I go x of a, and I set that to 1, right? And we look at our dictionary, it's just got one thing in it. And now if I tell it that x dot a is 2, x still only has one a key in it, right? It's uniqueified the keys for me. It doesn't have 2 a keys in there. It's unique. Okay, so we're going to use a dictionary and see if we can do even better time here. Now the main problem we have is, since we had to check before whether or not our element was unique before adding it to our list. But this time, if we use a dictionary to add stuff to, right, we don't even need to do the check in the first place, right? We just know the dictionary is already going to sort it out for us. All we need to do is try and add the key into the dictionary, and the dictionary will go, oh, yep, cool, I'm just going to overwrite this key, or this is a new key, and it sort of handles it for us. So let's set this up again for item in items. Now all we're going to have to do here is make a new key in our dictionary where item is the key. So the actual value here isn't really that important at all. I guess we could make item the key as well. So that we have something like 1, 1, 2, 2, stuff like that. But this is actually going to uniqueify our thing straight up for us, right? Because all we need to do is go, well, chuck it in as a new key. And we know we can't have duplicate keys in the dictionary because the dictionary will just overwrite them as we go. So this is much simpler. But we wanted to return a list of numbers, right? So we should probably set up an actual list, right? And we know we have that result dictionary contains a list of all our unique keys now. So all we need to do is we need to just get the keys out. Okay, so if you guys remember, the .keys method for a dictionary will give you something that you can iterate over, which basically just gives you back all the keys in the dictionary. Okay, so if every key in the dictionary, well, we're just going to stick it in our result list, right? Cool. So there's our result list with all our keys in it. And then I guess at the end of the day, we just want to return that result list. Okay, so let's have a go on that one. Uniqueify 3 this time. And yeah, we can see that that's got our new keys in there perfectly fine as well. Okay, so let's just sort of recap on what's happening here. For every item in items, we're chucking them into this result dictionary here. I'm actually just going to print this out. Let's print our result dic just so we can sort of see exactly what's happening here. Okay, so we can see we added all the items into the dictionary key. Into the dictionary as keys. And this is our result dic here, and we can see that all the keys, 2, 3, 4, are unique, right? Because that's just how the dictionary works. Okay. And so at the end, we just go through and we just grab out all of those keys and chuck them in a list. And that's what we're doing here. So let's have a think about the time complexity here. So for item and items, well, we've looked at this a bunch of times now. So we should know that this is n counts, right? Because items is n long. So we know that to loop over every item is going to take something proportional to n. So there's our linear time, as we were talking about before. Okay. Now to assign something into that list, oops, why is I doing that? Why can't I tab there? Okay, that was weird. To assign something into that list, well, that's just a constant operation, right? It just takes a single count. We're just going, cool, chuck this in the list. It doesn't need to loop or anything like that. Setting up a blank list is the same. And now we're looping through everything in our result dictionary keys. Now you might be thinking again, well, the result dictionary keys can be smaller than the items that we started with, right? But remember, once again, we're looking at the worst case. Okay, now the worst possible case in this instance is that our items is already completely unique, right? In which case, this result dictionary keys is going to have every single item from items in here as well. So in the worst case, this guy can also get up to n counts, which is also like you can be linear, right? It's going to scale linearly. And then once again, just chucking a single thing into a list doesn't really do anything. It's just a constant operation. We just go bam, one thing's in the list, right? So, and then we're just returning, right? So let's do our little maths down here again. So that first loop is n times 1, because every time we do this thing n times, and every time through it we do this single count operation here. And then same again here, right? Every time through this loop we do n times, and then times 1. Okay, so both of these are linear sort of operations. And if you kind of want to think about it this way, you can sort of see that this would add up to something like 2n if we were sort of just counting all the steps. Now, like I was saying before, we don't care about this constant here, right? This 2. We don't care if it's 2n or 3n or 1n or 60n. The point is that it's a linear function, right? It's linear time, and it's scaling directly proportionately to n. Okay? So the thing you got to think about is quadratic time, right? So it's n squared. And you might think, oh, well, if I've got something that's 2n, maybe this is slightly worse than n squared. And that's actually, it's sort of the wrong way of thinking about it, right? Because just because there's a 2 here, you have to think about what's going to happen as n gets really big, right? Because that's the reason we think about complexity, right? When the problem's really big, we want our algorithm to still run in a decent amount of time. So if you think about if n was 1 million, right? 2 million, well, that's not that much worse than 1 million, right? But if you think about what 1 million squared is, well, that's a massive number. That's significantly worse than 2 million, right? So if you can sort of count up all the steps in this way and arrive at a kind of function or a sum of them, like we did here and here, you can sort of work out what kind of time it should just be based on the end, right? So even though we had 2n, this is essentially just linear time n. Because, well, 2n is a linear function, right? And that's one way of sort of calculating the time complexity as you go. Now, one thing that we don't really cover in this tutorial is logarithmic time. And I'm going to give you guys a quick example of it just to sort of show you an example of logarithmic time, right? So let's just get some space here. Now, my example is just something I thought of earlier, so it doesn't really have anything to do with this tute. But let's just suppose we had a list of sorted numbers. I don't know, maybe duplicates are allowed, and that's all fine, right? And we have this list here. Now I'm just going to describe an algorithm, and then I'll show you why it's a logarithmic time, right? And then hopefully that's enough, because we didn't really cover logarithmic time over here. So say I want to determine if the number 12 is in this list, right? So one thing we could do is we could just go, well, you know, for every item in this list items here, right? We could just check, is the item 12? Right? And that would be a perfectly valid way of doing this, right? But how is this going to work? It's going to check this guy, then this guy, then this guy, then this guy, and it's going to go all the way along, right? And let's say that 12 isn't in this list, right? It's going to check every single number in this list before it determines no. So this sort of algorithm here is actually, it's linear time, right? Because how many times is this items and items going to do? Well, we're looping over everything in the items, right? So in the worst case, this is going to take n counts, and so we've hit linear time. Now, this algorithm doesn't really take advantage of the fact that our list is sorted. So let's try and have another go at this. If I want to know if 12 is in here, right? Let's just hypothetically, let's just cut a line right down the middle of this list. Okay? And let's look at this 9, right? Let's say this 9 is the middle element, roughly, right? And we look at this 9. Since the list is sorted, right? If I know that 9 is here, can I possibly have a 12 on this side of the list? I can't, right? 12 is bigger than 9. So if there is a 12 in the list, it's going to be on this side, right? So in that sense, if I just check the middle number and I see that it's a 9, I can basically cut half my list, right? In other words, I've already halved the size of my problem only in a single step. Okay? And then, you know, likewise, once I've cut that half, I then do the same thing here. I check the half number and I go, oh, cool, is there a 16? And I go, cool, half is 16. So I can go, well, 16 is bigger than that. So everything on this half is gone because I know it can't be a 12, right? Because 12 is less than 16. And then I check the half number again. There's only 2 things left. So let's just say 11 is the half. And I go, cool, is 11? Oh, I go, well, 11 is smaller than half. So get rid of everything to the left of 11. And then I'm left with one guy, and I go, oh, well, there's only one guy left, right? So I go, is this 12? And he's not 12, right? So I know, well, 12 was never in my list to begin with. And so this is logarithmic time, right? If I use this sort of approach here, because think about what I'm doing. Every single time I do a single sort of step of the algorithm, I'm halving my list, my sample size of the list. If you think about how the linear one works, every single time we go through it, we're sort of looking 1. We're taking 1 out of the n elements away. So it's going to take n time. But if we think about this thing here, it's actually a logarithmic sort of equation because we're halving it every single time. If the size of my list doubles, right? Let's say I go from 1 million elements to 2 million elements. This algorithm here, where I'm sort of halving everything, is almost going to be unaffected, right? Because it's literally just one extra split that it has to do. And so this is why this is why logarithmic time is such a desirable thing compared to linear time, right? Because it scales so much better. Think about, like, if I have a number 1,000, right? And then I take the log of 1,000. Well, the log of 1,000 is 3 if we're working in, say, log base 10. 3 is a lot smaller than 1,000, right? And as that number gets bigger and bigger and bigger, the log number is only going to get smaller comparatively. So that's why logarithmic time is such a good thing to think about as well. Okay? So if you get to your exam questions, or you're sort of looking at an algorithm and you can see that every single step through the algorithm kind of takes out a fractional chunk. So when I say a fractional chunk, for instance, here we were taking out a half every single time, right? But it would still be logarithmic time if we were taking out a third every time, or even a tenth of the list every time. As long as we're always taking out a designated fraction, the complexity is still going to be logarithmic. Okay? And then once we've got that out of the way, we basically know that, well, this part of the loop or this part of the algorithm is logarithmic. The only other thing you need to think about when doing your complexity calculations is remember that when we're adding stuff up or we're dealing with constants or anything like that, it doesn't matter about any of the constants, and the only thing we care about is the worst possible thing here, right? So for instance, we had n log n plus n, so the worst guy is n log n, right? We always think about the worst case, so we say it's n log n time complexity. So let's say, hypothetically, you went through and looked at some other algorithm and you determined, oh, yep, it's going to take 3n squared plus 2 log n steps plus another n steps, right? We look at this guy here and we might go, oh, cool, he did this part really well with log, so the time complexity is going to be better, right? Well, no, we don't care about this log part because there's a big ugly n squared over here, which is much worse than any of these. So the only term we care about in this case is the n squared term. And like I was saying before as well, the fact that there's a 3 here doesn't really mean anything because it's just a constant. The only thing we're really concerned with is the n part. Okay? So even though there's all this other stuff happening here, this algorithm would be quadratic time because we always think about the worst case. Okay? Yep, that's basically the sort of long and short of time complexity, okay? Like I was saying before, there is the course notes section here on complexity and computability. You can go through and have read that. It's a bit more technical, a bit more specific. I've tried to sort of just cover it more with examples and stuff. But obviously you can refer to this if you have sort of more specific technical questions. And as always, if you have any other questions about the video, feel free to drop them on Piazza. Feel free to drop a question in the comment section below. And otherwise, I wish you guys the best with your exams, and yeah, good luck with the rest of the course.